to get to this mission of imaging the whole Earth every day.
If we can do that, then we can literally change the way that we see the world.
And they called it the Dove. It's about the size of a loaf of bread.
Our doves are basically mainly a big camera with a telescope looking down to take pictures of the Earth. We initially developed the first Dove satellite in our garage. So we kept on iterating the Dove design, we made it better and better, and eventually we put our first one into space. We had no idea what the quality would be like.
I mean, we didn't know if it was going to work.
But we got an image down and it was so beautiful that we knew at that point we could make this technology work.
Wow, we can really do this, and we can achieve this mission, which is something that is really needed for us to understand global change.
So we had done a couple of demonstration satellites, but the next steps we wanted to do was to scale it up, to test the first fleets of satellites.
But what made that possible was actually access to space.
So here's the problem, that in order to take pictures of the entire Earth every day, you're going to need more than one or two satellites. You're going to need a whole lot of satellites, and you're going to need to be able to deploy them really fast. And really, there's only one obvious choice on how to deploy that, and that's the International Space Station.
There was no other platform in the world in order to get access to space of that fashion in that time period than the International Space Station.
NanoRacks is our key partner with NASA.
At NanoRacks, we understood Planet Labs' vision, and we knew that we could help. We worked together to figure out what was going to be the best way to get as many satellites as possible, and we basically developed a new platform. It goes out of the GEM airlock. It's picked up by a robotic arm, pointed out into space, and it fires these little satellites off of the space station.
They were able to secure 28 of our satellites to be launched from the International Space Station, and that was known as Flock 1, our first constellation.
This opened up the whole world to satellite developers, people that could put things into orbit fast.
We now deploy these on a regular basis from the International Space Station. And now today, we're able to operate the largest fleet of Earth imaging satellites in human history.
And none of that would have been possible without the International Space Station.
The International Space Station does enable young, small companies like ourselves to get going in space.
The ISS provides a lot of opportunities for commercial companies to test and find where the market in space is going to be.
And so what we're seeing today is a proliferation of new ideas and new concepts. It's almost like it's a renaissance of what's happening in space. Buckle up and strap down, because this is going to be a rocket for all of us in the global community to be part of.
The first pictures now coming in from Puerto Rico after taking a direct hit. Hurricane Maria slamming into the island. One official saying the island is destroyed.
Hours with winds and rain, and didn't stop.
Power lines are down, streets are impassable, many roads are flooded.
High winds uprooting trees, overturning cars, and turning buildings into piles of twisted metal.
It is something that will change Puerto Rico forever.
We had no water, no food, no gasoline, no communication at all.
Not knowing where my next meal will come from, it hasn't been easy.
After Hurricane Maria, everything was gray, all the plants were dead. Hurricane Maria took the color away from us.
I am sure that these children will not be the same. They will not be the same. They are still struggling and trying to recover from this.
My name is Joe Acaba. I'm a NASA astronaut of Puerto Rican descent. I was about a week into my mission on the International Space Station. Hurricane Maria was forming up, and from there, if you looked out the window, Maria took up a big chunk of what we could see. It was going to cover the entire island. After the hurricane, their power grid was pretty much taken out. You just couldn't see the island anymore. The hurricane, I think, had a huge impact on, the island as a whole, but especially the kids.
Joe Acaba was our hero, and we need something positive. The students need something positive.
We wanted to pull through, forget all that happened, and lift up our spirits and lift off the island.
So I knew I couldn't do much from up on the International Space Station, but I did want to connect with the students to show them that there is hope and that there are people out there that care about them.
NASA has the STEM station, which allows the students and teachers to talk to the astronaut in the space station.
It's making that connection so that maybe, they become more interested and we can inspire them more to study the STEM fields.
So we were able to establish and coordinate with NASA one of these video conferences. Thousands of students from different parts of the island watching the video conference with the space station, talking to Joe.
This is Joe aboard the International Space Station. I have you loud and clear.
How do you compare?
What is the most impressive view? How did Puerto Rico look after
astronauts allowed to visit? How often?
What is the minimum number of?
It was awesome because, as soon as it came up, you could hear people clapping, people were excited. So even though I couldn't see them, I could feel them, and that was pretty neat.
It was amazing. He called from the International Space Station to see how Puerto Rico was doing, and that means a lot for us, a lot.
In May of 2018, I was able to go back to the island, my first time since the hurricane. It was a great opportunity to get out and kind of come full circle with those students, to go and see them in person and, kind of reiterate how important they are, and just to give them a little bit more hope because there's still a long way to go on the island.
He's a hero for us. Kids love him, and everybody loves him here. Joe Acaba is the role model that we need at this time.
I want to be like him. I want to go far, and I want to be an example for little kids when I'm older.
Not only is the International Space Station a great tool for scientific research and exploration, but for students from Puerto Rico in particular, I think that having that video conference with them, it did provide some hope. It did provide some inspiration. And so it's just one of the benefits that we get from the International Space Station.
To support International Space Station, we're constantly having to build new hardware to send to space, but as well, we need to make training hardware on the ground. So we ask ourselves, what if we got high school students to build us some training hardware and get them out of the textbook, get them some hands-on lessons to work with, and by doing that, we'll be inspiring the next generation of students. So that's when we decided to create Hunch. Hunch goes to the local high schools, partners with the high schools, and gives these students opportunities to design, build hardware that'll fly in space or be used for training hardware on the ground. Students did the design and engineering, the CAD drafting, the 3D print prototyping, the machining, the procurement of the hardware. All this done by high school students to get this article to fly in space. From the quality perspective, the students have exceeded all of our expectations. The hardware we're getting in is top-notch.
This program actually helps them focus into the engineering and the STEM fields.
I've been teaching for 23 years. I've never seen anything that even remotely compares to having the type of impact on students that Hunch has had. Absolutely phenomenal.
Working with the Hunch program, we fabricated training hardware for the ISS.
I created and designed interactive simulations.
We're making a Mexican paella and hopefully gets chosen to go to the International Space Station.
From the Hunch program, I've learned how to use AutoCAD,
and we learned a lot of teamwork.
I've definitely gained some communication skills.
We're learning more about food science, technology, but everything basically doing this.
It gives them a confidence that I don't think they would have had to that level before this.
Maybe I would actually be able to be an engineer. So it was never something that I'd thought that much about. And then I was working on this stuff that went to space, and I couldn't think of anything more exciting. And I still can't.
It's a pretty cool thing to be able to tell other people or family when you go visit that I work with NASA programs.
I mean, I told everybody, like literally everybody.
We have an opportunity here for them that is unbelievable.
It's kind of like getting a master's at age 16.
They truly have moved on to a level they wouldn't have approached or wouldn't reach, I believe, without this program and without the International Space Station.
Before the Hunch program, I really was just a C student with no direction in my life. And since then, I've been on the Dean's List for the past 4 years and will be transferring to pursue mechanical engineering.
It really helped me find my passion for aerospace. The Hunch program gave me my career.
The impact on their lives has been amazing. They're more successful, they're more driven, they're more determined. They know they can achieve, and that's all, I think, through this program, through the Hunch program and interaction with the International Space Station.
Today's telescopes study the sky across the electromagnetic spectrum. Each part of the spectrum tells us different things about the universe, giving us more pieces of the cosmic jigsaw puzzle. The most powerful telescopes on the ground and in space have joined forces over the last decade in a unique observing campaign known as GOODS, which reaches across the spectrum and deep back into cosmic time.
Hello and welcome to this very special multicast. We'll be exploring a unique collaboration between some of the world's most powerful telescopes, both on the ground and in space. Now to do this, we've set up a similar collaboration between the ESOcast, the Hubblecast, the Spitzer Space Telescope's Hidden Universe, and the Chandra X-ray Observatory's Beautiful Universe.
I'm Megan Watsky for the Beautiful Universe from the Chandra X-ray Center.
And I'm Dr. Robert Hurt for the Hidden Universe from NASA's Spitzer Science Center.
It's the combination of deep observations from many different telescopes that makes this project so important.
The longer a telescope spends looking at a target, the more sensitive the observations become, and the deeper we can look into space. But to get the full picture of what's happening in the universe, astronomers also need observations at a range of different wavelengths, requiring different telescopes. These are the key ideas behind the Great Observatory's Origins Deep Survey, or GOODS for short.
The GOODS project unites the world's most advanced observatories. These include ESO's Very Large Telescope, the NASA ESA Hubble Space Telescope, the Spitzer Space Telescope, the Chandra X-ray Observatory, and many more, each making extremely deep observations of the distant universe across the electromagnetic spectrum. By combining their powers and observing the same piece of sky, the GOODS observatories are giving us a unique view of the formation and evolution of galaxies across cosmic time, and mapping the history of the expansion of the universe.
Now this is not the first time that telescopes have been used to give us extremely deep views of the cosmos. For example, the Hubble Deep Field is a very deep image of a small region of sky in the northern constellation of Ursa Major. This revealed thousands of distant galaxies, despite the fact that the whole field is actually only a tiny speck of sky, about the size of a grain of sand held at arm's length.
Now, with GOODS, many different observatories have brought their powers to bear on two larger targets, one centered on the original Hubble Deep Field in the northern sky, and one centered on a different deep target, the Chandra Deep Field South in the southern sky. The main GOODS fields are each 30 times larger than the Hubble Deep Field, and additional observations cover an area the size of the full moon.
These areas of the sky were already some of the most extensively explored, and so the combination of the existing archival data with the many new dedicated observations gives us an unprecedented view of the history of galaxies.
At ESO's Very Large Telescope on Sierra Paranal, the 8.2-meter diameter giants were used for a total of almost 100 nights of dedicated observations. The telescopes made images of the region both in near-infrared light and on the boundary between visible light and ultraviolet light. At these short wavelengths, only telescopes on exceptional sites, such as the VLT's Sierra Paranal, have a chance to observe through the Earth's atmosphere.
The NASA ESA Hubble Space Telescope observed the GOODS regions at optical and near-infrared wavelengths in order to detect distant star-forming galaxies, among other things. Now, Hubble spent a total of 5 days observing the fields, spread over 5 repeat visits. Each of these was separated from the previous one by about 45 days. Now, by spreading out the observations like this, Hubble was able to watch out for new supernovae appearing over the months, providing key information for studying the expansion and acceleration of the universe due to the mysterious dark energy.
But it wasn't just Hubble making space-based observations for GOODS. NASA's Spitzer Space Telescope imaged the GOODS regions in near and mid-infrared light for 5 days at wavelengths up to 30 times longer than the Hubble observations. These longer wavelengths are important for revealing distant galaxies whose light may be obscured by cosmic dust or stretched by the expansion of the universe, making them invisible to Hubble. For these distant galaxies, the Spitzer images also tell astronomers about their age and their total mass of stars, complementary information to the data from Hubble. Now, let's move from the infrared to much shorter wavelengths.
Also in orbit, the Chandra X-ray Observatory had already observed the GOODS field in many long observations taken over the course of a year. The Chandra images are the deepest X-ray images ever taken and detected more than 200 X-ray sources believed to be supermassive black holes in the centers of young galaxies. The X-rays are produced by extremely hot interstellar gases falling into the black holes.
These multi-wavelength observations identified tens of thousands of galaxies. To get a full understanding of the history and development of galaxies over the vast stretch of the universe's history, we need to be able to pin down their distances more precisely, to fix them in cosmic time. As these galaxies are so far away, the light waves we see from them today started their journey up to about 13 billion years ago. And because the universe has been expanding since the Big Bang, back then the universe was less than 1/7 of its current size.
During the billions of years of the light's journey, its wavelength has been stretched as the fabric of space has expanded. This effect is known as redshift because, for example, light that was originally blue or ultraviolet in color is shifted to longer and redder wavelengths.
Back on the ground, astronomers used spectrographs on ESO's Very Large Telescope to capture the spectra of galaxies, spreading out their light like the colors of a rainbow. Now, the spectra allow astronomers to measure the redshifts of the galaxies and hence their distances. An extensive campaign produced redshifts for almost 3,000 galaxies in the GOODS fields. Now, with this knowledge, we can place the galaxies at their distances along a vast cone of space, stretching out from our own vantage point like a searchlight beam into the cosmos. We can take an amazing journey through kind of a tunnel towards the edge of the universe. In some places, the galaxies cluster together, forming structures which are up to tens of millions of light years in scale.
Thanks to GOODS and other surveys of the same region, these areas of the sky are uniquely well studied, with high-resolution, deep observations across a wide wavelength range. Plus, there's more to come. For example, the Atacama Pathfinder Experiment Telescope, or APEX, has spent a total of 300 hours, nearly 2 full weeks, imaging the region at sub-millimeter wavelengths from its high site on the 5,000-meter altitude plateau of Chajnantur in the Chilean Andes.
Observations at these wavelengths are ideal for finding the redshifted light of distant, dusty galaxies in the very early universe. Because of the longer wavelength of its sub-millimeter light, the APEX image is not as sharp as the visible light and infrared images. However, thanks to the deep Spitzer images, as well as images made at radio wavelengths, we can match up and identify the objects found by APEX with galaxies seen at other wavelengths. The sub-millimeter light glow reveals that hundreds of stars are being formed per year in these galaxies. In the next couple of years, ALMA, the Atacama Large Millimeter Submillimeter Array, currently under construction on the same plateau as APEX, will begin its first science observations. Also observing at submillimeter wavelengths, it will have much greater sensitivity than APEX, and resolution even better than Hubble. ALMA will revolutionize our understanding of the early universe by revealing many more distant, dust-obscured galaxies that cannot be seen at all by visible light and infrared telescopes.
These projects are an excellent example of how great observatories are joining together across the electromagnetic spectrum to give us a more complete view of galaxies over the history of the universe. Already, astronomers have written over 400 papers based on these data, with even more in the pipeline. And on top of that, the observations of the GOODS fields will continue in the future. These patches of the sky will be prime targets for the next generation of telescopes, both on the ground and in space. And astronomers around the world will use these data to learn new things about the universe for many years to come. This is Dr. J, signing off for the ESOcast and the Hubblecast.